Okay, welcome to the second part here, which we're going to go on to logarithmic law. Now, logarithmic is something not new to um, AMAT student because they already done so. But for them to really explain what is logarithmic law is could be quite challenging. So in this case, I'll attempt to first explain what's the use of logarithmic uh, functions. Okay, and it is uh, easier for you to understand later. Okay, so let's begin by having a function or an equation. So as most of you, in fact, I think all of you should have gone through what we call a simple algebra course in lower secondary. So if I have y equals to 2x plus c as an equation, sorry, let's don't use c, let's use a number instead. Okay, you know that it is a graph, okay, with gradient 2, meaning if for every 1 here, the y increased by 2. Alright, that will be the gradient. Okay, but the intersection is at 3. So we start off from 3. For every increase in y, it raised by 2 points, which is 2. So 4 and 5 here. So with this, you draw a straight line from here onward. That's how you get this thing. Now, if the graph is a straight line, we call this a linear graph. So it's very easy to represent linear graph because for every increase of it, we should see the straight line graph having in this sense. But what happens if the value is not something like this? If the value is something like y is equals to 2 to the power of x. So what happened here is, let's try to plot the graph nicely inside here. Okay, so when x equals to 0, remember 2 to the power of 0 is 1, so it's 1. So this is 0, and this is x, this is y. So when x is 0, y has the value of this. Now when x is equals to 1, then y has the value of 2. Okay, when x is equals to 2, y has the value of 4. When x is equals to 3, y has the value of 2 to the power 3, which is 8. So let's try to plot this thing accordingly. 1, 2, 3, 4, 5, 6, 7, 8. In this sense, and this is 1, 2, 3. So it started from here. When x is equal to 1 is 2, which is quite okay. When x is equal to 2 is 4. When x is 3 is 8. So you see that the graph actually goes up tremendously, very steep here. So what happens if you want 2 to the power 4, 2 to the power 5, 2 to the power 6? Your graph, you need to have a very lengthy y in order for you to see the graph. Now, this kind of representation is not suitable for data visualizations. Okay, say for example, I just increase a knob, say in my volume control. This is a volume control. Okay, if I increase one knob, one segment, okay, the sound increased by 1/4. From here, it jumps 1/4 up the amplitude. If I increase one more knob, increase twice the previous one, which is about here. So can you imagine you have a lot of knobs going on, and what? The volume increase what we call very steeply. In this case, we call it increase to the power of 2, a factor of 2 exponentially. Because for every knob increase, it increase by twice. So for this kind of representation, it is very difficult for us to draw it on a graph and very difficult for us to represent in values, because we say that, okay, the the volume at this knob is now 100 units. Now when you turn the next knob, it becomes 200 units. Okay, so far still good. If you turn the next knob, now it becomes 400 units. Then the next knob becomes 800 units. The next one is become 1600 units. So for every increase, the increase is so steep that it's very difficult to represent the to see the changes at the high end and changes in the low end. So with this, scientists created a scale called the logarithmic scale. Logarithmic scale. What does it mean is, okay, look at the scale here. You see this scale in the normal frequency domain equalizer. Okay, so it may start off from, let's say 1 or 0 rather. Okay, 1. Okay, then the next segment what you have is 10 here. All right, so the next segment is 10 to the what square, so it's 100. The next segment is 1000. Now each scale is divided into 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each segment here is 10 units. Now when you go past the 10, the increment is no longer 1. Sorry, each increment is 1 for the previous one, my mistake. Now this is 1, okay, 2, 3, 4, 5, 6 accordingly. Alright. Now when you increase to the next one, it's no longer 10, it is 20, 30, 40, 50, 60, 70, 80, 90, 100. So each of these become 10. Okay, and then here is increased by 100. So it's 100, 200, 300, 400, 500, 600, 700, 800, 900, 1000. So each scale here is increased by 100. Now why do scientists want to do that? Remember, when during beginning, the increase of y is very little. But as the value goes, for every increment, okay, it has a sharp value. So if we were to plot it in logarithmic scale, all right, what happens is we can represent very large values changes over here or here, depending on which scale we do, all right, and it's represented with a small increase of this. So if we were to plot this in reverse, in reverse of this, not the x-axis, but now the y-axis itself. Okay, let's try. We start from 1 first. The origin is 1. And then here is 10. And here is 100. I'm sorry. My fault. Okay, I'm supposed to do the reverse here. This is 10. This is 100. This is 1000. So I have x equal to 1. When x equals to 1 or x equal to 0, if we start from 0, it's alright, but usually we start with 1. X equal to 1, the value is 10. X equal to 2, the value is 100. X equals 3, the value is 1000. X equal to the value of 4, this one will be what? 10,000, right? The value will be 10,000. So you see, given a linear increase in value, we can still observe the what? The increase in the y, all right, in a linear phase. All right, so regardless, despite the fact that we have a small increase in y, we don't get a very steep increase in the value of y. Now take note that the actual value of y actually increased. It's just that we use a different scale to represent y so that visually, or rather mathematically, the change appear coherable. That means we're able to see the changes in a more in an easier perspective. All right, so this is the purpose of logarithmic scales. Okay, so with this logarithmic scale, I'm going to go on to the second part later, which is called the logarithmic law. Okay, so thanks for watching and watch out for the next video.